Morning, sir, and all my classmates. Today we are going to present STORM, an efficient stochastic transformer-based world models for reinforcement learning. My name is Wong Jing, and these are my teammates. And this is what we are going to discuss today. So STORM is an architecture that leverages a VAE and incorporates a GPT-like transformer as the sequence model to improve modeling quality and accelerate training. STORM established a mean human normalized score of 126.7% on the Atari 100K benchmark, while requiring only 4.3 hours of training. Deep reinforcement learning often suffers from low sample efficiency, particularly in challenging real-world environments. This stems from two reasons: the difficulty of approximating the value function and the limited useful training information provided by sparse rewards. Model-based DRL attempts to resolve these limitations by constructing a parameterized simulation world model using self-supervised learning, such as reconstructing input states or predicting actions. By leveraging the model's imagination capabilities, the agent's policy can be enhanced without the constraints of real environment sampling. However, this autoregressive imagination process accumulates prediction errors, leading to discrepancies between imagined and real trajectories, which can cause the agent to pursue virtual goals. Introducing random noise through stochastic methods like variational autoencoders help mitigate this issue. Previous world models often rely on RNNs, such as LSTM and GRU, but the recurrent structure results in slower training speeds. Although the transformer architecture overcomes these challenges, attempts like TWM and IRIS often fail to surpass GRU-based models or require longer training times. Other RL methods like Efficient Zero and Speedy Zero incorporate Monte Carlo tree search, which enhances policy but has high computational demands. This summary table briefly shows the comparison between STORM and other recent approaches. Now I'll pass on to next teammate.
Good morning, Dr. Go and my friends. Now we will go through the world model learning, and in this session we will cover these three things. So before we go through the world model learning, we will do some briefing. So the world model is like the model can understand the real world or your environment, and then it needs to predict based on the this action to predict the future observation. And then so this is the causal reasoning. So based on this action, I will see what in the future observation. So the agent can learn the policy in the world model without the real environment. Now we go to the method of collect the data. So the agent policy will be enhanced in the world model, and then we train the world model using the data from the cube replay buffer, and then the data collected through the interaction with the environment. So in each time step, we will call data observation, action, reward, and then the continuation. The continuation similar like the termination. And then we will store this raw data into the cube replay buffer. So before we go through, we'll introduce some components. So the first is the variational autoencoder architecture, the encoder and the decoder. And then for the encoder, it needs to generate the latest stochastic categorical distribution, and then the input is the real observation, and then the decoder need to recover the observation. So the input is like the LSCD, the ladder variable will sampling from the LSCD, and then you use the ladder variable to reconstruct the observation. And then the third is the sequence model. The sequence model has like the RNN, LSTM, and then the GRU, and then transformer, and so on. And in this article, he used the GPT-like transformer, and then the input like it combines the action and then the random variable into a network, and then we call the action mixer, and then the action mixer will send into the transformer, and then it will generate the hidden stack. And then the other is like the dynamics predictor, reward predictor, and then the continuation predictor, all based on the multi-layer perceptron. And then this is the structure and imagination process of the stuff. So in the beginning, we will send the observation one into the encoder, and the encoder will generate the Z1, the resampling the random variable from the Z1, and then we combine the action into the transformer blocks, and then the transformer block will generate the hidden set. We based on this hidden set needs to determine the continuation, and then the reward, and then the next distribution. And then the next distribution needs to send with like the observation tool through the encoder Z2. And then we sampling from here, and then we continue combine the action as a token, and then send into the transformer, and then the hidden stack, and then we repeat this process, and then we use the hidden stack with the agent, and then the agent needs to apply the policy. Then the policy later my teammate will explain more, and then we repeat this process. And then but the third frame begin the third frame, we don't need the encoder. We only use the hidden stack based on previous frames hidden stack, and then we sampling from the Z3 sampling from here. The random variable will sampling from the hidden stack generate here. And then we repeat the process. And then now we go through the loss function. So for the BAE architecture, we train with a reconstruction loss. And then the reconstruction loss, we use the Obsidian distance. The Obsidian distance will calculate the predictor observation and then with the real observation difference. And then second is the reward predictor. The reward predictor will calculate the sync log to hot loss. The sync log to hot loss is like you convert the regression problem to as the categorical problem. And then the next is the continuation predictor. The continuation predictor use the binary entropy loss. And then next is the dynamic loss and the representation loss. All of these are use the KR divergence. And then for the dynamic loss, it learns to the how to predict the next distribution like this. It needs to learn how to generate with SEM with the Z2. This 2Z2 is the SEM. And then the representation loss needs to allow the output of the encoder and then to be quickly influenced by the influence model prediction. So for this tool, it needs not the independence, it needs to dependence. So it needs to weekly dependence on here. So he trained with this loss function. And then last is the total loss function. The total loss function, we combine these 5 things. And then for the dynamics and then representation loss, we use the hyperparameter, fixed hyperparameter 0.5 and then the 0.9. And then now I pass the time to Wai Hong. Thank you.
Hi, I'm Tan Wai Hong. Now I'll talk about how the agent learn. So the agent are using a actor critic based learning method. So it contains 3 key elements, which is the state. It is concatenated by the sample Z and the H. And the critic will be the expected value of the return, and the actor will generate the probability of the action. Here is how they calculate the actor loss. First, the term G lambda means the lambda return, and the lambda return minus the V, the critic value, means the advantage. So it means that when the policy sample action with a better advantage, with a higher probability, then the loss will be smaller. After that, the H term will be the entropy loss, so that the policy can be more explored. And for the lambda return, when the lambda equal to 1, it means that it's the one-step TD return. And when when the lambda equal to 0, it is the one-step TD return. And when the lambda equal to 1, it is the normal Monte Carlo return. And the S term is simply for the normalized purpose. So for the critic loss, it's simple. If you want to the critic want to learn about the value of the lambda return. So there is a square arrow there, and the next term will be the net value minus the moving average term value to prevent the critic learn too fast.
To test the model, they use a benchmark called Atari 100K, which consists of 26 different video games, and see how well the model play these games compare with other models. For the evaluation matrix, they use something called an agent's human normalized score, which has this formula. Basically, what this formula tells us is the inverse slope between a random policy and a human. So if it has a score of 0, it means it plays as good as a random policy, and if the score is 1, it means it plays as good as a human. So there are some games the model is good at and some games the model is bad at. The model performs well in games such as Miss Pac-Man, Chopper Command, and Golfer. This is because the objects related to rewards are large or multiple. For example, as you can see in this screenshot of Miss Pac-Man, not only there's a lot of different important objects such as the character, the ghost, the food, and the gods. The model also needs to keep track of the velocity and direction of the character and ghost because this information is also very important. This model outperforms other models because the autoencoder is able to capture the key components of all these multiple different objects, and the transformer is able to keep track of these objects between frames, such as the speed and direction of the characters and ghosts. This is because a transformer is great at handling long-term dependency. However, the model performs poorly on games such as Pong and Breakout. This is because for these 2 games, right, the most important information is only a single moving object, which is this tiny ball over here. So this means that when you input this frame into an autoencoder, 99% of the information will be useless. And also, since in variational autoencoders, each token is sampled from a distribution, it adds even more randomness into the latent component. Furthermore, the attention mechanism from the transformer may amplify the noise generated from the autoencoder instead of the real signal. Therefore, in a game where you need to precisely locate the ball's location and its velocity, having this much noise and randomness will cause the model to perform very poorly.
Good morning, sir. Now I will talk about the selection of the agent state. We know that the choice of agent state provides some options such as hidden state, stochastic latent variable, and the combination of both. If the environment requires good policy in contextual information, the inclusion of hidden state leads to improved performance, while in the other environments, such as Pong and Kung Fu, the inclusion does not yield a significant difference. Solely utilizing hidden state in environment involved with agent policies such as Pong may exhibit behavior similar to catastrophic forgetting. Next is the impact of the demonstration trajectory. The implement of trajectory in environment with sparse rewards such as Pong and freeway may improve the robustness, while in the environment with dense reward may hinder the policy environment of the agent. So we know that to achieve the first reward is extremely difficult, so the trajectory may act as an instruction to gain initial exploration direction to train the world model and establish starting points for imagination. So in future, demonstration trajectory may use as utilization of limit offline information and serve as specially designed curiosity-driven exploration strategies. So the conclusion of the STORM model is it's surpassing previous methods such as Rainbow and PPO in both training and performance. STORM model harness the powerful sequence model and generation capabilities of transformer structure while fully exploiting its parallelizable training advantages. STORM model broadened the applicability of it while reducing the computational cost. Although the STORM model has provided many advantages, it still has some limitation. It is trained in end-to-end fashion, so it only can predict its own internal output, introduce additional non-stationary, impedance scalability. Secondly, on-policy distribution is not explicitly considered as the starting point is off-policy while the action and agent is in on-policy. That's all for our presentation. Thank you.